Hi, I'm Joe Sawiki, and I'm Vice President and General Manager of the Design to Silicon Group at Manufacturability. This includes aspects around physical verification, optical proximity correction, as well as design for test. You know, the phrase design to silicon, I once handed a business card to someone and he said, well, that's pretty much everything, isn't it? I said, well, our emphasis is on the two. It's on that transition from that ideal world design over to the reality of physics and semiconductors. So we concentrate on verifying that handoff to manufacturing, drawing out what potential issues could occur in those designs, as well as testing those and providing that information that comes from tests back into the design flow to increase yield over time. The biggest challenge can be pretty easily summed up. It's like, how do we continue with scaling? If you look at the conversation has very quickly moved from scaling being a ubiquitously good thing to where customer after customer is debating, do they move to the next node or not because of the cost issues. So finding ways where we as an industry can innovate together to ensure that scaling can continue to provide cost, performance, and functionality benefits to the end user is the best thing we can all do together to ensure the health of this industry. So from a literal perspective, the word EDA is electronic design automation. Conceptually, what we do is provide software that allows the design and manufacturing chain to navigate its transition from the layers of abstraction that belong in a design. You start off with these very high-level descriptions that are written in high-level modeling languages, and at the end you end up with transistors switching at gigahertz frequencies. How you then give the designers the ability to model what those layers of abstraction do, whether or not you're reliably moving from each one of those layers, and then providing the software that ties that all together in such a way to make the thing work, that's where we come in. Our main focus on the litho side is what we call either RET or OPC software. Here what we're doing is we're modeling the physical process of imaging a mask onto a resist process, and then providing software that allows us to produce a mask that will give you the designer's intent at the end of the day. Which means we have to work very closely with a lot of different providers to make this happen. So design for test is conceptually easy. What it is software that allows us to insert circuitry into a design that then allows us to, in a cost-effective fashion, figure out whether or not that device works once we're done with the manufacturing process. And so it's all based on things called scan design, where we train all of the state elements in the design together, present test cubes to that, move it forward, check the thing out. Now, the lithography connection is not obvious, but what's interesting about that is because you're doing all of that, you get to learn an awful lot about what's working and not working on the design. And if you can collect that information statistically over large data sets, you can start to point to, I've got chips that fail, 5% of them, and they all point to a contact issue that's occurring in a certain place, which lets us then explore what is the pattern issues that are occurring around that contact. And so it's a way of feeding back, essentially turning production designs into virtual test chips that give us more information back in the lithography process. People talk about how design process is no longer limited by random defectivity. It's limited more by systematic defectivity. The problem is every single issue of systematic defectivity starts off life hidden as a random defect. You've got a problem, but you don't know what it is. This allows you to find out what that problem is and bring it into an area where you can do improvements in the process. So hopefully this isn't something you're finding on a daily basis that you're not doing contacts well, but rather you will episodically through a process discover that some intersection between the design and the process is causing a particular issue that then you can modify out of the process. If you march up and down that design and process stack, there are opportunities where going from step to step, you'll flip someone from a competitor to a partner to a competitor to a partner, back and forth the whole process. Things work well when we're all aligned, if it's pre-competitive. You know, people who are doing work on 7 nanometers at this point in time, there's a lot of easy cooperation there because it is so impossible to do at this point. You come back a little bit to the current processes and things start to get a little bit tenser. But I think we've all evolved to the point where there are cooperative areas of research institutions we all work together at. There are companies who have formed consortia, things like the IBM Alliance where companies can come together and work on this. And for the most part there are good APIs and interfaces along the way that tool integration can happen reasonably well. So I have people who are trying to take away my entire market who I'll still be talking to on a Thursday about how we work together to make something happen at 10 nanometers at this point in time.